Welcome to KTU Mathematics, and today we are going to learn KTU Semester 2 Mathematics. From KTU Semester 2 Mathematics, I have chosen Module 1 for the first topic, and in this video we are going to study these much portions. Here you have seen that Textbook 1 is preferred for studying Module 1. And you know what is Textbook 1? This is the preferred textbook of KTU, so you can just go and pick it up from the library. There is also another textbook for this. This is textbook 2 of KTU Semester 2, and this textbook 2 is preferred to study Module 4, 5 and 6. When we get to Module 5 and 6, I will explain it to you. So keep in mind that this textbook is the preferred textbook of KTU for studying calculus of vector function, and from it these all sections are necessary and we are going to study it. So let us get on to the topic. Okay, first we are going to start some basics of vectors. We know that a vector in 3D space can be written as a1 cap plus a2 cap plus a3 cap. This is a vector in a 3D space. It means that when we draw the 3D space, x, y and z, the vector will be a1, a2 and a3. It will be from origin. So that's what it means. Likewise, I am also going to write vector b so that I can do some vector calculations with it. Okay, I hope you know that there are so many calculations that can be done in a vector. That is, the first one is dot product. Vector A dot vector B can be written as A1 into B1 plus A2 into B2 plus A3 into B3. And likewise, vector A cross vector B can be solved by this matrix. First row A1. In the first row we can write I, J and K. In the second row A1, A2 and A3. In the third row B1, B2 and B3. By solving this matrix you will get vector A cross vector B. I will solve it now. First of all, take this matrix. You have to multiply these elements and then multiply it with I cap. I will do it now. A2 B3 minus A3 B2 into I. What we have to do is take these elements and multiply it with J. I will do it now. A1 B3 minus A3 B1 into J. Please note the minus sign here. Then we have to take these elements and multiply it with K. I will do it now. A1 B2 minus A2 B1 into K cap. This is the answer of vector A cross vector B lessons. Now we can go to the next slide and study the next lessons. Now we can learn the equation of the angle between vector A and vector B. Angle between vector A and vector B. That is cos theta equal to vector A dot vector B by magnitude of A into magnitude of B. Magnitude of A can be found out by root A1 square plus A2 square plus A3 square. Likewise, magnitude of B can be found out by B1 square plus B2 square plus B3 square. Okay, by substituting this into the denominator and calculating this, you will get cos theta. Out of that, you can find theta by theta is equal to cos inverse. You have to write that answer here. Likewise, you can find the answer for theta. We have to also learn some identities related to vector calculation so that we can progress in each chapter. Now I will teach you that. Note, I am going to teach some identities to you. A dot B is equal to vector B dot vector A. Vector A cross vector B is equal to minus vector B cross vector A. Vector A cross vector A is equal to 0. When vector A is parallel to vector B, A cross B is 0. When vector A is perpendicular to vector B, vector A dot vector B is 0. These are the identities you need to learn. Now we can go to the next section. Now we can further move on to the portion vector valued function of single variable. Now we can write a function f equal to xi plus yj plus zk. This is a function in a 3D space. Now suppose that f is governed by t, x is also governed by t, y is also governed by t, that means it is controlled by t, and z is also governed by t. That means that the whole equation is of single variable. When t changes, the whole equation changes and it will create some patterns in the 3D space. That's what it means. Function of single variable. The equation is governed by a single variable, and in parametric form the same equation can be written as xt, yt and zt. This is the parametric form of the equation. When t changes, all the equation changes. So it is also called parametric curve. Curve means that when t changes, this equation will create some patterns in the 3D space. That's why it is called curve. Okay, now we can go to the next portion and learn how this t changes. Now let us write a equation and see how the parametric equations can be converted into a parametric curve. Now let us write the equation. The parametric equation is x is equal to 1 minus t, y is equal to 3t, and z is equal to 2t. Let us write the answer. Suppose the function is f and it is governed by t. Parametrically it can be written as 1t, 3t and 2t. Now when t is equal to 0, this equation becomes 1, 0 and 0. Substitute the value in t. When t is equal to 1, the equation becomes 0, 3 and 2. You just have to substitute the values of t in the equation. By substituting different values of t, we will get different parametric equations like this, and by having these 2 points, we can plot it in a 3D space. Let us plot it now. Okay, this is the vector we have obtained. This is x-axis, this is y-axis, and this is z-axis. This is 3, this is 1, and this is 0.2. So the vector we have obtained is 0, 3, 2, that's this point, and this point is 1, 0, 0. Likewise, with n number of points, we can have many equations, and thereby we can extend this vector. I hope you understood this problem, how a vector equation can be converted into a parametric curve. Let us go to the next problem. Now let us go to the second equation. The parametric equation, metric equation, is x is equal to a cos t, y equal to a sin t, and z equal to ct. This can be written as a cos t, a sin t, and ct. By looking at the c function, we know that when t increases, z will also increase. Okay, suppose this is the 3D space. This is z-axis, this is x-axis, and this is y-axis. When t increases, z will also keep on increasing in the upward direction. But please note these points. This is the parametric equation of a circle. So we know that when t increases, the function will go on like a helix, like this. This is the meaning of this parametric equation. I will show you graphically this equation. Before we move further into new portions, let us look the problem we have done just now. For parametric equation a cos t, a sin t, and ct, that's the equation we have done just right now. And I will show you how it's plotted in 3D space with a software. This is how it look like. And as A increases, the circumference of the circle will increase, and with C increases, it will extend upwards. Now A increases. Look. I will show you now when A decreases. It will also decrease, and with C it will extend upwards. That's what it is. And now let us go to the next portion. Now let us better understand what is vector valued functions. We know that a vector f governed by t can be written as this. And by substituting values into t, we got vectors and also points. In the first problem, we substituted t equal to 0 and t equal to 1, and we got 2 points. From t equal to 0, we got 1, 0, 0, and from t equal to 1, we got 0, 3, and 2. This is a vector, and we connected both these points and formed a vector. Now let us better understand vector valued functions. Vector values function can be denoted as R, and it is governed by t, and it has the same equation. But there is one difference. First let me write that equation. But there is one difference. Here we substituted 2 points, but in vector valued function only single point is needed. And where do we get the other point? It is the origin. Vector valued functions are vectors that start from the origin and end in a point. It's a single point. Here this point or this point is needed to define R. Now let us check a figure and learn better from it. And this was the question we did first, and we found 2 points and connected it to create a vector. But really in vector valued functions we only need 1 point. 1 point is the origin, and the other point we need to connect. Let us connect it now. We made 2 vectors. The first vector R1 and the second vector R2. The origin point and the end point is only needed for vector valued function. Such a function, such a vector in 3D space is known as vector valued function. From now onwards, when we say vector valued function, we mean that it is a vector from the origin to a point. And now we can learn the natural domain of a vector valued function and progress further. Now let us study the natural domain of vector valued functions. Natural domain . Natural domain is same as finding domain for any other functions. If you don't know how to find domain of function, just see our videos in the miscellaneous section about how to find the domain of functions. Then continue this topic. Now let us find the natural domain of vector valued functions. Question by question. We can do the first question. We know that the domain of trigonometric function is from -infinity to infinity, and we know that the domain of logarithmic functions is from 0 to infinity, and we can find the domain of this function. Now let us find it. Now we can find it one by one. Natural domain of xt is from -infinity to infinity. Please denote the open brackets. xt means cos pi t. Natural domain of yt is log t, is 0 to infinity. Log 0 is not defined. Greater than 0, log has a value. Only in 0, log is not defined. From 0 onwards, log has a value. So, the last question, natural domain of zt is, let us find it here. We have to equate it. It's t minus 2, t greater than or equal to 0, and the natural domain will be 2 to infinity. Please denote the square bracket here, closed bracket. So the natural domain of RT is the intersection of these domains. We can find it with a number line. -infinity, infinity, 0, 0, 2. So the common is 2 to infinity. So the natural domain of RT is, natural domain of RT will be 2 to infinity. It is closed bracket here, not open bracket. Now we can go to the next question of natural domains. Find the natural domain of So the answer will be natural domain of xt equal to, okay, we can find the natural domain here, 3t plus 1, 3t plus 1 greater than or equal to 0, 3t. Do you know why this root sign is cancelled off here? Because it is squared. Both sides we square and we get from this step to this step. Greater than is equal to minus t, t greater than or equal to 1, 3. Okay, now we can write over infinity. T of t raised to 2 is infinity to infinity. We know that the natural domain of polynomials is infinity to infinity. So what is the natural domain of RT? RT will be the intersection of these two. Intersection of these two will be. Okay, then we can go on to the next portion. Now let us study the limits of vector valued function. If you do not know how to find limits, please watch our video in the miscellaneous section. Now let us do the first problem. Let rt equal to t square I plus etj minus 2 cos pi t k. Find limit t tends to 0 rt. We can write the answer. First, rewrite the question. Now, while taking the limit, we have to take the limit of single terms. T tends to 0 etj plus limit t tends to 0 2 cos pi t k. Now we can put the limits to the equation. 0I plus 1j minus 2k. OK is equal to j minus 2k. That's the answer for this equation. And now if you do not know how to find limits of function and how to find the natural domain of functions, please check our videos limit t tends to infinity t square plus 1 by 3t square plus 2 comma 1 by t. Let us find it out. Answer. We have to give limits for both of them. T square plus 1 by 3t square plus 2 limit t tends to infinity 1 by t. Before putting in the limit, we have to rearrange the equation to get the correct value. We can take t2 outside from both the numerator and the denominator, and the numerator would be 1 plus 1 by t square and denominator would be 3 plus 2 by t square, and the second term will be as such. Now putting in the limits, first we can cancel these terms and we can put the limits. 1 plus 1 by infinity square, 3 plus 2 by infinity square, and 1 by infinity, and it will yield 1 by 3 0, because both these three terms will be 0 when divided by infinity. And we can get on to the next portion. We can do another problem. Limit t tends to 0 root t sin t by t. We can put on the limits. Limit t tends to 0 root t, limit t tends to 0 sin t by t. We can apply the limits on this equation straight away, but this, if the limits are applied, will yield 0 by 0, so it is an indeterminate form and L'Hospital rule needs to be applied. So we can apply the limit on this and it will become 0. We can put L'Hospital rules first. D by dt sin t by d by dt t, and it will yield limit t tends to 0 cos t, and the answer would be 0 1. This parametric equation can be also written as j because all other terms are 0.